We now switch over to Boston in the US, and we actually narrowly averted debacle because there's a power outage in Boston. So an hour ago, I was told that Butler is without power, and we were working on could we do it via the phone or whatever. It seems like the power is back, and we should be all good to go. At least that's what people tell me. So our next presenter is Butler Lampson, who is a researcher at Microsoft. Butler is, by any definition, one of the most eminent people in computing. And he's won many awards, but in particular the one that beats all the others, which is the ACM Turing Award, the computing equivalent of the Nobel Prize, for very good reasons. If you look at what's happened in computing, particular operating system and distributed systems in the 70s, 80s, it's probably faster to mention the things Butler didn't have his fingers in than the ones he did. What he was involved in is operating systems design, a very influential paper on the confinement problem, which is an issue that still plagues computer systems today. Everyone who's ever studied operating systems has heard about the access control matrix. That's Butler's creation. He's done a lot of work in distributed systems, especially authentication and access control, distributed consensus, distributed transactions, the MESA system, the Alto PC, and any number of other things that were highly influential throughout the years, and he's still active. So, for his talks on hints and principles for computer systems design, which is actually an update on a paper he's written a few decades ago, we welcome Butler Lampson from Microsoft in Boston. Please welcome Butler.
Hello. It's a pleasure to be here. I'm sorry that I'm not in cool, sunny Sydney myself. And I'm grateful that the power company has, at the last minute, turned the power back on. So we didn't have to experiment with doing this through the cell phone hotspot. So this talk is about a new paper that I've written, which, as Gernot said, is an update of an almost 40-year-old paper called Hints for Computer System Design, which I presented at the Symposium for Operating System Principles in 1983. This new one has not been published, but it is on archive, and you can find it there and in a couple of other places on the web if you just search for Lampson Hints Principles. The overarching theme for this talk, I guess, is that you should use a good idea again, or to put it another way, most of the good ideas in computer systems have many more applications than most practitioners are aware of. In 1983, an SOSP paper was a comfortable fit for what I knew about, in an informal sense, about how to write computer systems. I was able to put almost everything that I knew into the 20 or so pages of that paper. Today, unfortunately, I know a lot more, and the new version is closer to 100 pages, which is painfully long, but I think if you dip into it, you'll find that there's not a lot of scope for taking things out. I actually made a shorter version, which is only a little bit longer than the original paper, but it was very, very painful to decide what to leave out of the shorter version. So in order to make it a little bit easier to organize the various hints and in some cases principles that I have, I've made up this slogan, steady by aid. Steady refers to the goals that your system that you might have for your system. You might want it to be simple, timely, efficient, adaptable, dependable, and yummy. And aid refers to the techniques that you are at your disposal, or at least some of the techniques that are at your disposal for achieving these goals. with the exception of a few slides on principles, this talk is about hints. Hints are just suggestions. They might or might not be relevant to your system. They're not necessarily consistent with each other. They're not necessarily precise. Nitpicking hints is really not appropriate. If you find one that doesn't appeal to you, just skip over it and move to the next one. So here's the what, the goals aspect of things. You'd like your system to be simple. You'd like it to be timely. That is, you'd like it to get to market soon enough to be successful. You'd like it to be efficient and adaptable. You'd like it to be dependable. And finally, in many cases, it's important that it be yummy. Three of these goals, the ones in black, were also leading themes 40 years ago. The three in red all seem very important today, but they were really not very important in the 1980s. So that was the what. Now here comes the how. These are ways of achieving the goals. And I've organized them under three major headings. You can approximate, you can do things incrementally, and you can divide and conquer. And unfortunately, those are in more or less inverse order of importance. So when I talk about them, I'll do them in the opposite order. Before I start in on this, I'd just like to say a few overarching words. One is that I like to think that there are two different kinds of software in the world, which I call precise and approximate. Precise software has a spec, typically one that's written down, although not necessarily. And the most important property of a precise software system is that it satisfies its spec. So avionics software, banking, Microsoft Office, those are examples of precise software. Approximate software, on the other hand, it typically doesn't have a spec that's written down. Of course, it's possible to write an appropriately loose spec, even for an approximate system, but that really is not the way the customers think about it. The important thing for an approximate system is that you get it soon and that it's cool. So search, shopping, Twitter, those are approximate systems. I'm not trying to say, the natural instinct of the computer scientist is to say, oh, well, precise software is good and approximate software is sloppy and bad. That is not what I'm saying. I don't think it's true that one kind of software is better or worse than the other, but I do think it's true that they're very different. And if you don't realize what kind you're writing, you're going to get into trouble because you're either going to do too much work to satisfy a spec that the customers don't really care about, or you're going to do too little work and fail to satisfy a spec that the customers do care about, depending on which kind of software it is. Another overarching point is this one. There's a tremendous amount of value in choosing the right coordinate system. It's like using the center of mass coordinate system for dynamics. Oh, they promised us severe thunderstorms, and you might be able to hear it in the background. Just started. Or choosing the eigenvector coordinate system for matrix calculations. So a simple example of this is you can think of a function as a table where the first column has the input values and the second column has the output values. Or you can think of a function as code that computes the output value from the input value. Or you can think of a function as an overlay where first you try one thing, and if it doesn't work, you try another thing. And of course, it's possible to express, at least in principle, it's possible to express any function in any of these ways. But depending on what kind of system you're building, one or another way of looking at it may be a lot better for you. Closely related to choosing the right coordinate system is choosing a good notation. The most striking example of this that we see in computer systems is domain-specific languages. And the reason that domain-specific languages succeed is that for choosing the right notation for your problem has an enormous amount of payoff. On the other hand, the right notation for writing abstract specifications typically is not any domain-specific language, but instead is the mathematical notion of relations, which subsumes sets, functions, graphs, programs, and the basic operations on relations of composition, transitive closure, union, and intersection as primitives give you a very powerful language with which to say what it is at a high level that your system is supposed to be doing. But they're not very helpful for saying how the system should go about doing it, because typically the language of relations is much too inefficient if you try to directly reduce it to what the execution of what the computer is good at executing. So just a little bit more on this coordinates point. We already talked about 3 different ways of looking at functions: as a table, as code, or as an overlay. A more subtle example is that I'm very fond of is that you can think about the state of your system as being or as becoming. So the being state is a map. You give me a variable name, and I give you back the value of the variable. And that's the usual form. That's the way we usually think about the state of a system, which is more or less a direct reflection of the fact that the computer memory has the property that it works that way. You give it the address, and it gives you back the contents of that location. The other way of thinking about a system is in terms of becoming. Starting from some initial state, what sequence of operations did we use to get to where we are now? This is not a very good way of finding out what the value of the variable x is, but it's very good for undo, for versions, and for recovery. And so these 2 ways of looking at the system state are almost complementary to each other. And I've illustrated in somewhat cryptic form in the diagram. The upper part of the diagram shows a sequence of 3 states viewed as being, and the bottom part shows that you can rearrange that data structure to be inspired more by the notion of becoming. Okay, I promised hints and principles, and I'm going to say a few things about principles. These are not, in my opinion, not like the hints. They are not optional. They are not things that you can take or leave. If you don't do these things, chances are your system is not going to come out very well. So the first of these is the most important one. Write down a specification. And the first step to writing a specification is to write down the abstract state of your system. There are a lot of people who think that this is kind of pointless because they say abstract state is not real. The only state that's real, they say, is the bits and bytes in the memory and on the disk. I find this viewpoint completely incomprehensible because from the point of view of the device physicist, those bits and bytes are completely artificial. The only thing that's real is the flow of electrons through the silicon. So it's just not true that abstract state is not real. It's just as real as any other state. So the canonical example that I'm going to use several times in this talk is the state of a file system. At the highest level, a file system is a map from path names to arrays of bytes, which are the abstraction of an array of bytes is an abstraction of a file. If you're going to write down the state, you need appropriate tools for this. And typically, as I said before, the appropriate tools come from discrete math. And almost all of them are variations on relations. Sets, functions, graphs, these are all versions of relations. My view is if you're not able to write down the state of your system in this kind of language, then you really don't know what you're doing. And it's surprising, in spite of that, it's surprisingly rare that people actually do this. And it's even more rare that it shows up in documentation that's intended for the clients of the system, which makes it very difficult to figure out what the system is actually going to do. We'll skip over the last point. Okay, once you've written down the state, the next step is to write down the actions. So a good first step into writing down the actions is to name them in some meaningful way. And then you want to say what each action does. So here's an example quite different from the file system example. If you want to specify failures, typically there's 2 operations that are directly relevant to failures. One is called crash, and the other one is called recover or synchronize. And what crash does is it takes the volatile state of the system and sets it to the persistent state. Or to say it another way, it throws away the volatile state. Now what sync does is it sets the persistent state to the volatile state. This is the sink that you are friends with from the Unix file system. And that, at an appropriate level of thinking about it, that is the whole story of what crashing and sync do. Of course, the code is going to be much more complex, and it's going to have lots of things to say about logs and index structures and all kinds of things. But at the high level, that's the specification for crash and sync. The tools for writing actions, in my view, are the fundamental tool is first-order logic, because an action is a relation between an initial state or pre-state and a final state or post-state. And you can always write this relation as a predicate on state pairs. This is not a very familiar way of doing things from the point for programmers. Typically, the programmer likes to write x gets the value of y, and what is the corresponding relation? It is x prime, the post value of x, is equal to y, the pre-value of y, and for any variable other than x, the post value is equal to the pre-value. From this point of view, program statements are a notation, and relations are the fundamental meaning. And if you want to see worked out in careful detail exactly what it means to connect a programming notation with relations as the meaning, you should look up Leslie Lamport's PlusCal language. Okay, before we plunge into the question of how the spec gets implemented, just a few words on what the spec is good for. The important thing about the spec is that it's, first of all, it's much simpler than the code. And secondly, it decouples the code from the client. So from the implementer's point of view, it tells you what you have to code, and it tells the client exactly what the client needs to know. And now the client and the code can evolve independently. Typically, a successful spec will have many clients, and a good spec can have many different implementations and different pieces of code. Widespread examples of this are the x86 instruction set architecture, this basics of an operating system's file system, or HTTP. Okay, so that was specs. Now, what about code? How do you write down the code, and how do you connect the code up with the spec? Well, that basic idea for writing down the code is you do exactly the same thing for the code state and the code actions that you did for the spec state and the spec actions. You say what the possible states of the code states of the system are, and you say exactly how each code action transforms one code state into another. So, reverting to the file system example, Unix file system code has data blocks, index blocks, directories, caches in the RAM, and all kinds of other things. From this point of view, what does it mean for the code to be correct? What it means is that every possible code behavior that the client can see is a behavior that's allowed by the spec. This is a fairly unfamiliar and fairly profound notion if you haven't run across it before. And the only way to really become comfortable with it is to look at a lot of examples. Once you've written down the code state and the code actions at some appropriate level of abstraction, now what you do is you write the abstraction function, which tells how it is that the code implements, how the code state implements the spec state. So the abstraction function, given a code state, tells you what the corresponding spec state is. And you also have to write down the invariant that describes what states are reachable. How do you know that you've gotten the abstraction function right? Well, in order to find that out conclusively, you have to give the proof that the code implements the spec. So let's just look at the different stages of writing down this proof. We've already gone over almost all of them. First, you write down the state. Then you write down what each spec action does. Then you write down the code state and the code actions. Then you write down the abstraction function, which tells you how it is that the code state is representing the spec state and the reachable state invariant. And finally, you show that each action on a reachable state preserves the abstraction function. So if an action takes code state S to S prime, then the same action in the spec must take code state F of S to code state F of S prime. And then by induction, it follows that any history, any behavior, any sequence of states that the code can take on is going to correspond to a sequence of states that the spec can take on, where the visible actions are the same. Now, there's a reason why I wrote these things down in successively smaller type. And the reason is that there's successively more work and has successively less payoff. And actually doing this proof is seldom worthwhile because it tends to be very labor and detail intensive and not that important for actually getting your system to be correct. Although in some cases, if the code is especially tricky or the reliability of the system is especially important, it might be worthwhile. But the initial steps are extremely worthwhile. And as I said, they get to be less and less worthwhile corresponding to the way the code, the size of the type is getting to be smaller and smaller. The reference I give at the bottom of the slide to a paper about how Amazon Web Services uses formal methods is a good example of how to make this work, which is very much grounded in a lot of practical experience. Okay, that was principles. Now we're going to talk first about methods and then about goals. So as I said before, I've classified the methods under three headings: approximate, incremental, and divide and conquer. Divide and conquer is by far the most important, and we'll look at it first. The most important form of divide and conquer is to divide the system by function. And the way you do that is by having abstractions with carefully specified interfaces. And the reason this pays off is that it limits the complexity that you have to think about at any one time. And it liberates the parts to evolve independently. So classic examples of this that have been successful for decades are TCP/IP, file systems, and HTML. All of these have lots and lots of clients and multiple implementations with different properties of trustworthiness, efficiency, and longevity. Other aspects of this notion of abstractions with interfaces, you want to organize your interfaces into layers or platforms like an operating system, a browser, a database, the x86 ISA, and so forth. And this is purely a matter of pragmatics. If you're going to actually ship things, you can't ship too many things or the customers will get confused. And so you have to organize the large number of modules that your large system is likely to have into a much smaller number of things, typically called, as I say, called layers or platforms, for the purpose of getting them shipped. Whenever possible, it's good for both the specs and, for that matter, the code to be as declarative as possible. Good examples of declarative systems are HTML, SQL queries, and database schemas. And the distinguishing characteristic of a declarative system is that the program that you have to think about only takes a few steps. Of course, the program that the machine is eventually going to execute is going to take lots and lots of little tiny steps: load, store, add, multiply, branch, and so forth. But we're not very good at thinking of the consequences of hundreds of millions of tiny steps. We think much more effectively about if the transitions of the system, if there are only a few steps that the system is taking to get to where we want it to go. And the final thought about abstractions is that in many cases, it's possible to synthesize a program, the code, that satisfies the spec from even a very partial spec. Classic examples of this in the modern world are machine learning and the Excel flash fill feature, which can synthesize a piece of string processing code from just a few input-output examples. And the paradigm here is you have some sort of signal that tells you whether your program is doing a good job, and you have some way of searching through the space of possible programs. And if you put these two things together, you can come up with a program if you're lucky. This is a very powerful technique when it works. And I think one of the big outstanding challenges of programming for the next 10 years or so, maybe even longer, is going to be figuring out how to extend the scope of program synthesis and combine these two currently radically different ways of doing program synthesis, machine learning and so-called inductive programming. Other aspects of divide and conquer, besides interfaces which divide by function, one of them is to be recursive, you divide by structure. And the basic notion here is that you should treat the part in the same way that you treat the whole. So examples of this: quicksort, distributed hash tables, path names, IPv6, file systems. Another way to divide is by performance, and the essential idea there is concurrency. And we'll talk about a lot more about that later. Big examples of successful examples of concurrency are BitTorrent and MapReduce. And finally, you can divide for redundancy either in time or in space. You're going to either retry, as for example TCP does, or you're going to do replication, which is a fascinating topic, which unfortunately I don't have time to talk about today. So that was divide and conquer. That was the D in aid. Now for the I in aid. I stands for incremental, and there's various aspects of incremental, and I'm just concentrating on two of them here. The most important one by far is indirection, where the notion is to control the mapping between names and values. That is the fundamental mapping that defines the being state of your system. There are many different ways to implement this kind of indirection. Just a few examples are virtual methods in object-oriented programming, copy on write, symbolic links, virtualization, virtual machines, network address translation, USB I/O bus. Most people don't know this, but when you connect a keyboard to a computer using USB, it turns out that what's actually going on is that the USB transport protocol is encapsulating the old IBM PC keyboard protocol, more or less bit for bit, and transmitting all those bits to the other end where they get unwrapped from USB and treated just as they were 40 years ago, and so on and so forth. The other I that I want to touch on is the notion of iteration. You can iterate the design, you can iterate your actions, you can iterate your components. So for example, there's redo, where the notion is you're taking a bunch of steps, you write them into a log, and if something goes wrong, so that you're not able to complete saving the state, you can go back to the log and do the actions again. Undo is sort of the same thing in reverse. If you take snapshots or abort transactions, that's a way of backing up from the steps that you took. And of course, scaling system so that they can handle bigger loads is a classic example of iterating the components. The internet, compute clusters, and multiple IO devices connected to a single machine are all examples of that. That was incremental. Now what about approximate? This is probably the least important of these three major headings for techniques, but that doesn't mean that it's not important. The underlying idea behind many kinds of approximations is that you don't have to get the right answer, you only have to come close enough. A good enough answer is all you need. So the web itself, search engines, IP packets with best efforts delivery, those are all examples of doing approximately the right thing, which is in fact good enough. Now, what I like to say about the web is that the reason it's successful is that it doesn't have to work, because the fundamental assumption is that the web's client is a person. And this is the explanation of why it is that when you try to make the web's client be a machine, you have to be extremely careful, because the thing is not designed to work all the time, and machines typically are not very comfortable with that. Another kind of approximation is to have loose coupling between components. The old slogan for networking is you should be liberal in what you accept and conservative in what you send. My slogan for that is flaky, springy parts. Email is the canonical example of a loose coupling system. And there are lots of other important examples of approximation that I'm going to skip over, but you can read all about them. So that was techniques. That was how you can build your system. What about your goals? This is a repeat of the slide where I introduced the goals earlier. Simple, timely, efficient, adaptable, dependable, and yummy. And we'll just look at all of them, one or two of them in more detail because they seem more important. So why do you want your system to be simple? It's because we can't do much. The obvious question to answer then is your simple system enough? And the answer to that is it's simple enough if you can still understand it. But if you can, just because you can understand it now, doesn't mean that you're going to be able to understand it a year from now after you've added a lot more code and a lot more features. When the system evolves, the only thing that's going to save you is abstractions and interfaces, because those are the only techniques that we know of for keeping the parts simple enough that you can understand them as the whole gets bigger and bigger and involves more and more people and more customers. Keeping things simple is hard, and often it's not rewarded because once you've made something simple enough, people will say that's obvious, even though in fact it wasn't obvious at all. And this, in my opinion, is the explanation for why it took us a physicist rather than a computer scientist to invent the web. So it's slightly overstated, but I think it's fair to say that if you'd written an SOS paper about Tim Berners-Lee's original web design, it would have been rejected on the grounds that it was much too simple-minded, and there were many opportunities to do things much more efficiently. My own opinion is that Tim got it exactly right. Simple is something that's been important from the very earliest days of computing, because from the very earliest days, we've been in a state in which it's very easy for us to make things more complicated than we can understand. Timely is something that's new since the 80s. And the reason, of course, that it's new is that now we have much better ways of distributing software systems and software-based services much more quickly than we did in those days. The web is successful, as I said, because it doesn't have to work. Efficient, I'm going to spend a little bit more time on this one. The most important thing is to make sure you understand that your system needs to be efficient enough. It doesn't have to be optimal. In fact, much more important than being optimal is that the performance should be predictable. You learn in your introductory systems course that the way to measure efficiencies in terms of the costs, which are time and space, which basically nowadays correspond to communication and storage. And the one formula that you need to know that has to do with efficiency is the fast path formula, which says that the time to get something done is going to be the time to get it done the fast way, plus the probability of having to do it the slow way times the time to do it the slow way. What that tells you is that your system is going to slow down from the fast way by 1 plus the probability multiplied by the ratio. So if you don't remember any other formulas, just remember that one. And the other thing to remember about efficiency is what I call the ABCs. Algorithms, you should shoot for algorithms that are n log n. Beyond that, you should shoot for the simplest algorithm you can find. Approximation, we talked about that in the context of techniques. Sampling, randomization, getting 90% of the way to the perfect answer. Batching, take big gulps. This is a variation on the fast path idea where the per item cost is the fast way, that is the cost of just doing the work without any overhead, plus the costs of the overhead, the per batch overhead divided by the batch size. It's the same formula. Caching, the basic idea is you have some fast function that doesn't always work, and you overlay that on a slower function that does work. And of course, you can stack that up and cache several layers deep. The tricky thing about caching is that when the state changes, you may have to update or invalidate the fast function. And finally, there's concurrency. And the slogan for concurrency is shard, stream, or struggle. Concurrency is really important nowadays. It's been forced on us by a combination of the cloud and the looming end of Moore's law. So there are two easy ways to do concurrency. One is to shard, i.e. have disjoint variables with no shared state. And then everything is very simple and the only limitation is the budget. And the other way is streaming, where the only shared state is producer-consumer buffers that connect one computation with the next one. If you can't figure out how to either shard or stream, then you're going to have to struggle. And there's several different ways to do it. There's an easy way, which is make things atomic by using locks and the fundamental idea there is if you lock the variable before you touch it, and don't unlock it until you're done with what needs to be atomic, then everything will be easy. And transactions are the enforcement are an enforcement mechanism that guarantees that you're doing this. Of course, at a price. If you're not going to do things if you're not going to shard, you're not going to stream, and you're not going to do things the easy way, then you're doing hard concurrency. And my rule for hard concurrency is very simple. You have two choices. You can do a correctness proof for your code, or you can have a bug. So hard concurrency is to be avoided. For that matter, even easy concurrency is to be avoided if possible, in favor of sharding and streaming. And finally, there's eventual concurrency, where you just let the updates dribble in. And this is very easy to code. And the problem with it is that the applications now have to pay the price because the state underneath your application now it is quite squishy because you don't know exactly which subset of all the updates it's seeing at any given time. The canonical example for eventual consistency, which is the one in which the ideas were originally worked out, is naming systems like DNS. Adaptable is another one of the things that's much more important now than it used to be. And the basic idea behind adaptability is you should plan for success. Your system is going to evolve, it's going to scale, and it's going to need various kinds of incremental update. And there are simple ideas for how to make your system more adaptable. The most important one, of course, is to have modularity. So the different parts of the system can change when that turns out to be necessary. A second thing that's really important for scaling is automation. There can't be any manual intervention if you're going to have thousands or hundreds of thousands of copies of things floating around in your system. And of course, the third key is concurrency, because that's the way you can increase the total amount of work that your system is doing without demanding that Intel make faster and faster processors, which they're not very good at doing anymore. And finally, dependability. That, of course, is often very important, but I don't really have time to talk about it today, so I'm just going to skip over it. And finally, there's yummy. Yummy means that your users really want your system. And there's two ways to achieve that, as far as I can tell. One is to make sure that the system has some function that the users really want, like spreadsheets, graphical user interfaces, the web, smartphones. The other way to make a system yummy is to do really good design. And this is, of course, Apple's forte. So that covers the ground. And I just want to wrap up with two slides that are quite tangential. One of them is trying to look into the future and ask, what are the different kinds of things that people do, that computers do? Computers started out doing simulation around 1950, and of course, they're still doing a lot of simulation. And it's been enormously successful. And for the first 30 years, it paid all the bills. Then around about 1980, computers got to be cheap enough that you could start using them to connect people. And that brought us emails and airline tickets and Bing and Twitter and all kinds of great things like that. And that's still going on. And it's now probably paying a lot more of the bills than simulation does. And the third kind of thing that computers do is they interact with the physical world. This started getting going, in my view, around 2010, and this is where the most exciting action is going to be for the next 20 or 30 years. Factories, automated factories, cars, self-driving cars, robots, smart dust. The computer is embodied in the physical world, and this raises all kinds of fascinating questions, of which I'm just going to touch very briefly on one, because it's something that I've been quite interested in myself in the last couple of years, and that is, how can we make it so that IoT devices, Internet of Things devices, don't kill people? This is not a huge problem now, but it's quite clear that it's going to be a problem as computer-controlled devices become more and more embedded in the physical world. And the basic strategy for this, in my view, is, first of all, you have to reduce aspirations and focus on what's really important. In this case, I've said what's really important is don't kill people. Everything else is secondary. Safe devices, from this point of view, need two things. They need a secure foundation, and they need a sound architecture. So the foundation means you have to be able to securely update them, isolate critical code. And there's at least one fairly carefully worked example of this in the world, which is a Microsoft product called Azure Sphere. But there's certainly nothing magic about Azure Sphere. There are a lot of ways to implement secure update and isolation for critical code cleanly enough that people who make IoT devices whose primary concern is not that kind of system building can actually use the foundation effectively. The other thing you need is a sound architecture, and the only one I've been able to think of is one in which you have a simple and very well isolated monitor that enforces safety. So simple means it has to be maybe less than 50,000 lines of code, that we know how to verify it. I'm not sure exactly how to define simplicity, but these are hints. The canonical example that I like to use for this is, suppose you want to make a computer-controlled traffic light. It's got cameras that look at oncoming traffic. It talks to neighboring traffic lights. It talks to the city traffic controller. There's 30 million lines of code there. How do we keep it from killing people? The answer is, it should never be green in both directions at the same time. And that's something that a simple monitor of much less than 50,000 lines can certainly enforce. And there's a couple of other properties that are essential for the monitor, but it's only half a dozen, not 100. The other reason, by the way, why this approach is really important is that most of this safety critical stuff is going to have to be outsourced, because IoT companies, for the most part, cannot hire first-class programmers because they can't give them a convincing career path. Okay, so that's the end of my story. Let me just summarize what I've said. This is an update of my 40-year-old paper. Unfortunately, it's much longer, but it's got lots more good stuff in it. And the slogan is study by aid. Keep things simple, timely, efficient, adaptable, dependable, and yummy. And approximate, do things incrementally, divide and conquer. And you're probably overwhelmed by all the things that I've said, which is only a relatively small fraction of all the things that I put into the paper. So if you only remember three things, here they are. Keep it simple, use abstractions with clean interfaces, and write a spec. And on that note, I'd be happy to entertain questions.
Thank you very much. Thanks for this very deep talk. There's definitely a lot of food for thought in here. We have a fair number of questions. Let's see how many we get through. So the one that won the most likes is, these days kids learn something called coding in elementary school. Can your hints and principles be encompassed in such teaching? What will be the outcome?
I don't know. I haven't tried to do that. Personally, I like teaching graduate students. I find it terrifying to teach undergraduates, because it seems to, in college, because it seems to me that I can do so much damage to the undergraduates. The graduate students are supposed to be able to take care of themselves, but I have a lot of responsibility for the undergraduates. And teaching elementary school kids, that seems even more scary. So I think this is a very good question, and it's worth a lot of thought, but I haven't given it any.
I have another good one. Here you specify a high mathematical literacy to define good design. With the very varied backgrounds of programmers today, is this a good assumption to have?
I don't really think that being able to understand relations demands a high mathematical literacy. What it does demand is gritting your teeth and spending several weeks working through the basic ideas and a whole bunch of examples. And it's very distressing to me that taking this tack is so unpopular in computing education. But I really don't think that this is easier than calculus, guys. And we don't say that engineers can't learn calculus.
Okay.
It's unfamiliar, but that doesn't make it that demanding.
Right. One which you partially answered, I guess, at least. Our new deep learning systems are approximate, probabilistic, but they're also being used in what you call precise, which seems bad in a car. Got any hints? I think you answered that on your third last slide, sort of.
That's basically my story. My view is if you're going to use machine learning in contexts where at least some aspects of the result need to satisfy a crisp spec, then you have to surround the machine learning with something that's not machine learning, that puts bounds on its behavior. And I don't think, we haven't yet given a lot of thought to the methodology for doing that successfully. Because for the most part, machine learning has been being deployed in contexts where it's not that critical, if the answer is wrong.
Yeah.
But certainly it is increasingly deployed in situations where it is critical. So I think I agree that this is a very serious problem.
All right. A related one, when we are timely, we often skip security aspects of our code since that works and fails silently. How do we address this issue?
This has been a problem for 50 or 60 years, and it's still a problem. I think there are a couple of aspects of this. One of them is that if security is, reset. In my view, the fundamental reason that we behave this way is that the consequences for insecure systems are actually historically have not been that bad. And therefore, people have not been willing to make upfront investments in security for the most part. They feel that it's much more important to have functionality or performance. As the consequences become more severe, if they do, people's willingness to spend more money on engineering things well in the first place is going to increase. But actually, my other angle on this is that I think fundamentally the most effective kinds of security are what I call retroactive security, which means you don't try to stop any bad thing from happening. What you try to do is weed out the riffraff of bad things and then make sure that if some bad thing does happen, you can do something about it. And there's basically two classes of doing things about it. One is putting the state back the way it's supposed to be, and the other is punishing the bad guys. And I think that we have by now accumulated a fair amount of evidence that tells us that for most real-world situation, this is far more effective than trying to make your system, quote, secure, unquote.
All right. This is an interesting one. Can one learn good design other than by experiencing the failures that result from designing things badly?
No. I think the best way to learn good design is to study well-designed systems. And this reminds me of something that I had meant to say about at the beginning of my talk, but forgot to, which is that this talk doesn't directly have anything to do with what John Lyons did. but indirectly it does because my view is that Unix version 6 is a textbook example of many of the things that I have been advocating. I do think that you also need to study some, maybe not experience, but at least study some examples of systems that didn't work out for one reason or another. But for the most part, I think the way you're going to learn these things is by looking at examples of system design that's been done well and trying to really understand why it is that a particular design is good.
All right. Another one, does a good spec reduce the need for high-level features in an implementation language, or does language expressiveness help in matching code to spec?
I think language expressiveness can do one of two things for you, neither one of which is directly related to matching code to spec. One of them is that it can mean that you have to write less code because the code that you do write is more expressive. And that has obvious advantages. It typically has some costs too, but it certainly has obvious advantages. The other, I've lost my train of thought, I'm sorry. Fundamentally, though, I think that the price you can pay for language expressiveness is that you lose some, typically you pay something in computing resources for the expressiveness. Not always, but in a great many cases you do. And the question is that a good deal? And the answer is, a great deal of the time, it's absolutely a good deal. JavaScript is an example of a language that has quite a lot of expressiveness and that pays quite a bit for it in a variety of ways. But nonetheless, it's been enormously successful within the domains in which it functions. On the other hand, if you want to solve partial differential equations efficiently, that's not a very good tool. Okay. So I think language expressiveness is a good thing, but it tends to be somewhat overrated.
Okay. Divide and conquer promotes many interdependencies to exist. How can we guarantee everything will stay supported?
Well, when you become the client of some existing component, that you're certainly taking a dependency, and that is risky. And it's risky for two reasons. One is that it might not be supported, and the other is that it might turn out that it doesn't actually do what you want, or everything that you want. I wrote a paper about this 15 years ago called "Only the Giants Survive," where I said that reusable components have been a dream of computing since the late 60s at least. And they have been enormously successful, but only very big ones have really been successful. And that basically has to do with business model. There's a high cost associated with building and continuing to support a component. And if the component is too small, there's going to be no business model for that. But there is a business model for database, something like a database system or a browser, because it's not an option to build your own. But for smaller things, typically you're better off, unless the smaller thing is part of some big thing that's been carefully designed and has longevity. For a smaller thing, you're better off copying the code and hacking on it. At least that's my view. Okay. And the reason for that, there's a fundamental reason for that, which is that every piece of code has embedded in it a lot of assumptions about the environment. How is memory handled? How are exceptions handled? How are other forms of resource allocation done? And on like this. And if you put several components together and they don't have the same model for the environment. You're going to have a mess.
Okay. Here's one that's a bit religious, which is probably not surprising given today's theme. Do you think that non-open source software hinders some of the principles you talked about? This one got upvoted very highly.
Do I think that non-open source software hinders principles? I think you can make a big mess in open source and you can make a big mess in closed source. And I don't really have enough hands-on experience with either one to be able to say which is more likely. Well, probably open source is better because the free market operates a little bit better in that environment. But I think this is a very secondary consideration. As I say, you can make a big mess either way.
I guess really open interfaces are more important in this context.
Yes, absolutely, which is why we should be grateful to the US Supreme Court for having told Oracle to shove it. The idea that you could copyright an interface is just such a brain-dead idea.
Fortunately, sanity prevailed for change in the courts here.
Fortunately, yes. This is another one of a long series of examples of the Supreme Court slapping down the Federal Circuit Court of Claims, or whatever it's called, which is the one just below it for patent disputes.
Okay, and the last one. With patching release software possible and easy today, it's less crucial to design, develop programs well before they are shipped. Any thoughts on this trend?
Yes and no. The big advantage of today's rapid distribution mechanisms, rapid and almost invisible distribution mechanisms, are that you can start small and grow. But I think if you start with a piece of junk, you'll never get any adherence. And so you'll never have any opportunity to do anything better. So no, I think it's still just as important, in many ways even more important, because the environment is more competitive. But it's just as important to do a good job on the thing that you ship. It's much less important to try to put in every possible feature, which by the way is a good thing for other reasons.
Okay, I think with this we are at the end. I'm so grateful for you to staying up at this started at 9 p.m. Boston time. So thank you very much, Butler, for your really deep and thought-provoking talk and speaking to us at this late time, and just very appreciative of your contribution here. Thank you very much.
It's been a pleasure.